and welcome to the Daily Space for today, July 29th, 2019. I'm your host, Dr. Pamela Gay, and I am here to put science in your brains. Today we have a variety of stories, but not as many as I expected. Yesterday I received a small flurry of emails just as we were getting ready to go live, and what I saw was press release after press release after press release, but because we were getting ready to go live, I didn't take the time to read them. And it turned out that what I thought meant a wealth of stories for today was, on further inspection, several press releases each for two stories that each wanted to demand a great deal of attention. The first of these stories is one that, takes a look at our sun. And what it's looking at in particular is spiral swirls that occur in the atmosphere of the sun over time. And hopefully this video will kick in momentarily. I appear to be having issues getting this video to load. What you should be seeing is patterns of swirls where the magnetic fields interact with the sun's outer layers. Have you listened to Flood? Not Flood, rather They Might Be Giants, where they refer to our sun as a mass of incandescent gas. It turns out that you can recreate this in a lab. University of Wisconsin-Madison graduate student Ethan Peterson has published results of a new experiment that recreates the sun's plasma spirals. He does this using a 3-meter bright red vacuum chamber, into which he and his collaborators added a very small amount of helium gas, the same type of gas that's in the atmosphere of our sun. And in this chamber, they heated that gas to 150,000 degrees. Now, the sun is more than just gas. To get the dynamics that, this video doesn't seem to want to let you see, they had to add in a powerful natural magnet, a bar magnet that was a cylinder 10 centimeters in length, 10 centimeters in diameter, and they also ran electrical current through this plasma to set it spinning. This model was able to recreate amazing features, including what is called the Parker spiral. This is where in the sun we see what appears to be a lawn sprinkler of spiraling out globs of plasma. They saw this in their sphere. The sun in a sphere model now, it doesn't fully recreate the sun's outer layers, but it is a simplified model that we can use as a starting point. The compositions in this sphere don't have the same diversity that we see in the sun. The densities are different, and in a system this small, we can't easily recreate the distribution of energies that the atoms in the gas are able to have. But while these differences affect the details in the model, it's still cool to see the big picture coming together in such a comparatively little experiment. So here is to, more experiments that recreate the sun in a great big red ball inside of a lab. Now, in other news, the TESS mission has, as it was designed to do, found more planets. At this point, I'm not sure that finding a planet alone is newsworthy. We have, after all, found thousands of them orbiting alien stars. What makes this particular discovery one that garnered 3 different press releases from Goddard, University of California, Riverside, and MIT is its 3 planets. Planets that are a little bit different than what we've been seeing everywhere else. In this graphic, which is remarkably not to scale, the star is not smaller than the planets, I promise. what we're seeing in this MIT press release graphic is representations of the planets to scale, but not to scale with the star. What they found is 3 different worlds. The innermost is 1.2 Earth masses and is considered to be a rocky world, and then 2 outer worlds. And here they're still snuggled in closer to what we see from Mercury than what we see from most of the planets in our own solar system. These 2 outer worlds have 2.4 and 2.1 Earth masses of material. Planets this world have been very rarely seen and not studied, really. And finding them here opens up a whole new area of research that can be done. This research, which was led by postdoc Maximilian Gunther, points out that this particular red dwarf star is actually fairly evolved. One of the things that we've talked about before is little tiny red dwarf stars like this one, during the first couple billion years of their evolution, have tremendously powerful flares and are very active. And all of this activity, well, first of all, it probably sterilizes the planets that are orbiting around it. But that kind of activity also causes the star to radically change in brightness, making it very difficult to do a lot of different kinds of detail-focused studies. Well, in this particular system, with this particular evolved red dwarf star, there is a constant brightness coming from the red dwarf. This consistency in light means that scientists are able to make measurements that usually are impossible, including measurements of these planets' atmospheres and potentially their radii and other qualities. This will help us in the long term understand how planets at these intermediate sizes are able to form. And what's really cool about this particular research is it may clarify if terrestrial worlds like our own Earth and Mercury and Mars and Venus have the same formation process as the larger worlds like Jupiter, Saturn, Neptune, and Uranus. Now, while these 2 larger worlds at 2.4 and 2.1 Earth masses are called sub-Neptunes, our own Neptune and Uranus are, well, 14.5 and 17 times the size of Earth, with Neptune being the 17 mass planet. And there's a big jump between 2.4 and, well, 14.5 Earth masses like we see with Uranus. So calling these things sub-Neptune seems like a bit of a stretch. But it will still help us see if those worlds form the same way as the terrestrial worlds, we hope. This is just a start. And hopefully this start will be able to constrain our theoretical models just that little bit more, and we'll finally be able to start understanding how solar systems actually form instead of making wild stabs in the dark that later turn out to be entirely not right, because, well, the universe is so often far more creative in what it does than what we are in trying to figure out what it does. Anyways, cool research coming to us from a myriad of different sources and discussing a small handful of really cool worlds. Now, in our final story of the day, I have a tale of what appears to be an experiment gone terribly wrong and the scientific sleuthing that was necessary to reveal this accident that it seems no one wants to talk about. Back in September of 2017, atmospheric monitors across Europe were able to detect low levels of radioactive materials from unknown sources. This cloud lingered through October and was carried by air currents in a plume that moved from east to west, as is shown in this animation of data from Romanian sensors. Analysis of this material found that it was rich in the radioactive material ruthenium-106. This element doesn't occur naturally on Earth. You don't find it in mining, but rather we create it in nuclear reactors. No nation at the time was willing to fess up to being responsible for this radiation. And theories that it could have been from a satellite, well, that was the main theory initially, but that theory was disproven by the data. It turned out that the radiation had higher concentrations at lower altitudes than higher altitudes. And if it was a satellite that broke up during reentry, you'd expect to see more radiation higher than lower. This meant that something was up at the surface of our planet. Not long after this plume was discovered, in a completely different sphere of influence, Russian scientists from the Mayak Production Association, who had promised to provide radioactive source materials to an Italian neutrino experiment, said in an email that was obtained by Science News and dated December 8th, 2017, that there was something unexpected. They wrote unexpected problems during the purification process of the materials they were planning to provide. What they were trying to make, cerium-144, can only be created by processing spent fuel from a nuclear reactor. And while processing spent fuel isn't a new process, we usually wait a fair amount of time before doing that processing, because when the spent fuel is first pulled out, it is extraordinarily dangerous and hard to work with. But to get that cerium-144, well, scientists were going to have to work with that not very safe fuel that is only a couple of years old. The ratio of 106 to ruthenium-103 that was observed in the plume, well, it was consistent with the processing of spent fuel that had been spent just 2 years earlier and was being processed. In a new study published in the Proceedings of the National Academy of Science and led by George Steinhauser, it is laid out how the timing of the Mayak failure to produce materials and the appearance of the radioactive plume over Europe seems to point at a nuclear accident that was small but nonetheless had a measurable impact on the environment. Had the processing not failed, Italian researchers would have been able to use the materials to search for the theorized sterile neutrino. Everyone involved knew that the processing of this radioactive material was dangerous and difficult, but pursuit of that particle, that sterile neutrino, drove everyone involved to try anyways. This kind of danger is often considered acceptable to scientists, and history is punctuated with experiments that had at least a few people asking, will this destroy this city, this planet, this universe? In this case, the risk wasn't that extreme, but the reality was this time things did go sideways, and instead of doing a physics experiment, we radiated Europe in a not dangerous but still not good kind of way. Given this publication, one would have hoped that Mayak would admit to what is believed to have happened. As of this story's writing, however, they are still denying the story. In a quote provided to Science News by Rosatom, the Russian agency that oversees Mayak, Rostom states, both the national regulator and experts from an independent international inquiry inspected the Mayak facility back in 2017 and found nothing to suggest that the ruthenium-107 isotope originated from this site. We may never fully know what happened. It could be that they're saying the truth and this is just one heck of a terrible coincidence. A lot of times it turns out the simplest explanation is right, however, and Occam's razor points to Mayak being to blame. We may never know what happened, but this is one of those times that says we really do need to reflect on what are the potential costs if things go wrong in the science we're trying to accomplish. And we need to remember to always ask, is the pursuit of that next great particle that may or may not be there, is the pursuit and the dangers inherent in that pursuit actually worth it? I don't know the answers, and I'm glad that I'm not one of the people that has to make these decisions. But I hope this does increase the amount of ethics training that goes in to, well, becoming a theoretical scientist. And that sums up the stories that we have for today. And I am now going to take your questions. I'm going to ask that you please type them into the chat and remember to @CosmoQuestX to make them easier for me to find. While you're typing those questions in, I'm also going to remind you that the Daily Space comes to you most Mondays through Fridays at 1 p.m. Eastern, 10 a.m. Pacific. That is 6 p.m. London time. If you miss us live here on twitch.tv, don't worry. Everything gets archived over on YouTube. You can find us at youtube.com/C for channel/CosmoQuest. We are here thanks to the generous contributions of people like you. If you would like to find out more about how you can support this show, please click on over to cosmoquest.org/donate. Your bits, your subs, your patronage over at patreon.com all work to keep us going and allow me to pay our staff to put this show together. Those of you who follow us over on patreon.com/CosmoQuestX, you will get my summary notes for each episode brought to you straight to your inbox. Now, we understand that not everyone can make a financial contribution, but there are lots of other ways that you can help us out. And one of the best ways you can help us out is to spread the word. Tell your friends, family, and, well, anyone else willing to listen that if they want to get a daily dose of what's going on in the world of astronomy, they should tune in to our show. We are actually looking into launching a podcast next week where we will be also releasing an edited audio version of each episode that will go out to our Patreon people and will also be released in iTunes and wherever else your podcaster may be catching its content. So stay tuned. We are always looking for new ways to make it easier for you to learn and do science. Okay, I am going to scroll back and see what questions you have for me to answer. And thank you, Wayne Johnson, for the bits. Thank you so much. Looking. Scrolling. No puppies today. Sorry about that, everyone. I actually do have Stella laying here next to me. Let me see if I can get Stella on camera so that you can watch a sleeping dog lie. Literally, that's what she's doing. She's sleeping like the dead right now, which is kind of cute. So there is the sleeping dog. I think I may have scrolled back to yesterday's comments also. Looking for more questions. Hello, Guido. Hello, Susie. Hello, Paranor. Hello, Larry. And yes, the net does love to repost stories over and over and over again. Hello, Wicked Wonder. I hope I was able to calm your soul, or at least feed your brain. So Larry, this wasn't a 3-meter vacuum tube. It was literally a 3-meter vacuum chamber that was a giant red sphere that they did this experiment in. I don't know about the meter-sized Celestron speaker. I don't know. Looking for other questions. Today, you guys seem to be low on questions, but Bill Nash subbed. Thank you, Bill Nash, for the tier 1 sub. Thank you so much. Yes, TESS did switch sky fields. This mission points for a little over a month at one of many different fields on the sky, so it just keeps switching through which area it's sitting on, cycling through. And what TESS is doing that is radically different from what Kepler did is TESS is surveying all the nearest stars, whereas Kepler looked at a wedge through space that meant that the bulk of what they were discovering was actually at greater distances. So this particular trio of planets that I talked about today is only about 75 light years away, making it one of the nearest solar systems that we've so far discovered. TESS is on a mission to find these nearby systems that we can do better follow-up with ground-based and other telescopes. TESS was actually designed to work in concert with the James Webb Space Telescope, but what is remarkable is they're finding ways to make everything work using the telescopes we've got instead of using the telescopes we anticipated. Henny is asking, if we could use nuclear propulsion in space, would it make space travel more dangerous for everyone else, or would it just be more radiation in a place with a lot of radiation already? I think it depends on how the system is designed. I have to admit I don't know a lot about nuclear propulsion. So that's really a question that's out of my bailiwick. Being a rocket scientist and being an astronomer are two radically different things. And in general, spacecraft are dead to me until after they've launched and become functional, because I don't want to get my heart set on any spacecraft that are going to cease to function as soon as they get to space, which is what happened to a spacecraft I was planning to use for my dissertation. So Annie might have a better feel. Our Instro might have a better feel. There's other people in our community who may know the answer. Binary Ablaze has questions, but they aren't related to the news. So Comic Girl is asking, what happened to NeoCam? I heard it's not getting funded. I don't know. Let me see if I can Google a quick answer. NASA has been restructuring a lot of its funding. So it's the Near Earth Object Camera. It's proposed to work in the infrared. So Congress mandated NASA in 2005 to achieve, by the year 2020, specific levels of search completeness for discovering, cataloging, and characterizing dangerous asteroids, according to the Wikipedia page. There are no new funds appropriated for this effort. Proposals for NeoCam were submitted in 2006, 10, and 15 to the NASA Discovery Program. In 2010, NeoCam was selected to receive technology development funds. And in 2015, the Discovery Program advanced NeoCam. At this point, it was not successful in 2017 for getting selected, but it was given an additional year of development funding, and NeoCam remains in the study phase. So it's currently in limbo. It is neither dead nor alive. I think that's probably the most accurate way to describe NeoCam. And missions can last a long, long time in purgatory. LISA is a mission that NASA had planned when I was still a graduate student. And now we're seeing the Europeans move forward with that mission, hoping to launch it in the next decade. So hopefully NeoCam will come back in one way or another with one nation or another. Let's see. Yeah, so Bill Nash is pointing out one of the confusing bits about talking about nuclear propulsion, and that's that there's two different models. One where you basically explode bombs out your back end using a shaped explosion that propels your spacecraft forward, and the other is to use the nuclear radiation to generate heat, which is what we already do in radiothermal generators. However, where radiothermal generators use that heat to power the spacecraft, In the case of nuclear propulsion, they use that heat to energize particles to high velocities that get jettisoned out the back of the spacecraft. So this is similar to a ion drive, but the mechanism for accelerating the particles is radically different. So Jay Sierra asks, how did you end up specializing in variable stars? I've heard from other grad students that the field they ended up doing their research in was often related to where they started working with a professor in their undergrad. Is that a similar story for you? Yes. So to step back a little bit further, I was actually really inspired by Timothy Ferris's book Coming of Age of the Milky Way, which has a section dedicated to talking about the women computers at Harvard College Observatory in the early 1900s. These women all ended up there from a variety of different backgrounds and for a variety of different reasons, and they really were the best and the brightest women of their generation. And among the many different things that they focused on was the study of variable stars, where we saw Henrietta Leavitt actually define ways to measure the distances to nearby galaxies using pulsating variable stars. And as a young woman growing up in a suburb of Boston and going into Harvard and MIT for a variety of different gifted and talented programs, I was one of those nerdy kids. It was just always cool to know that I was in the places those women did their work and pioneered their fields. Representation really does matter. Being able to see yourself in the science really does matter. And when I was an undergrad at Michigan State University, I started out working with one scientist doing projects using software I really hated, and I really wasn't interested in what I was doing. It was highly theoretical. And my second semester at university, I had as an instructor Horace Smith, who's one of the leading experts in variable stars. And I did an honors project for his class that led to a research position working with him in the future. And he was just a super good advisor. He had a super sarcastic and fabulous graduate student, Nancy Silberman, who was working with him. And she went on to work on the Hubble Key Project, which was one of those things that used variable stars to try and measure the Hubble constant back in the early and mid 1990s. And here I was seeing these things that I'd read about, so I hopped into doing more variable stars. Now, when I got to graduate school, there wasn't really anyone that I could continue that kind of work with at the University of Texas. So while I did do my master's thesis studying variable stars, I switched over to extragalactic astronomy to work with someone I really liked, John Cormandy, for my PhD dissertation. But I have continued to be an advocate of variable stars, and I'm currently waiting for a grant to do software related to variable star observations to get transferred. And when and if that ever happens, you will be hearing a whole lot more about variable stars around here. Okay, going backwards in the chat to see what other questions there are. I hope that answered Jay Sarah. Yes, work for the advisor who you get along with most rather than the person whose science is most exciting. You'll have a much better time of it. If you do science that you're excited with someone you end up hating, you'll end up hating the science too. So Larry asks, why does a CosmoQuest logo cover Pamela's face? Gone now. I have no idea. That must have been some weird thing that popped up on screen. Oh, it happens when you scroll over the screen. Sorry about that. So Bill is adding more information about RTGs, which he has clearly read a lot about. So go ahead and read what he wrote. It is good information. And thank you for the shout out. Yes, Bill Nash is another one of the educational streamers around here, and he's someone that I got to finally meet in person during the Astro Tours All-Stars party out at Joshua Tree, and he's an amazing photographer and just a good human. So go watch his stream. It's filled with pretty things, and you will learn about photography, Well, getting to go, oh, that's pretty. It's just, it's a happy place. It's a happy place. I'm glad that that was able to help Jay Sarah. So feel free to hit me up on Discord at any time. If I'm around and have time, I will definitely do what I can to help you sort options. But I think that does bring us to the close of today's episode of The Daily Space. As always, this is a production of the Planetary Science Institute, and it is brought to you by you. The Planetary Science Institute is a 501c3 nonprofit, and this means that your donations are tax deductible where the laws allow. And thank you for the bits, Trekker Kev. Thank you. We are here thanks to you. And we are also here thanks to the science you do. And if you have some spare time, if you're bored, please go map rocks. We are currently working with the OSIRIS-REx mission to map out the asteroid Bennu, which is one hell of a rubble pile. It is rocks and boulders, interleaved, stacked, grouped, piled. It's a rubble pile, people. And we have to map it so that we can find the safe place to do a touch and grab with our spacecraft as we sample its soils and bring those samples back to our planet Earth. So please join us at bennu.cosmoquest.org, and let's keep the science flowing. My name is Dr. Pamela Gay, and I'm glad that you joined me here today. And tomorrow, this show will be brought to you by our own Binary Ablaze, Annie Wilson, who will be doing a spacecraft update. And yeah, that's all I've got. So I am going to once again try and roll the persnickety credits that sometimes do not wish to be rolled. So let's see if the persnickety credits are willing to be rolled today. This is me awkwardly scrolling, because awkward is sometimes the only way to do things. So, wherever you are in the world, have a fabulous morning, evening, or afternoon, and I'll see you on the other side. Bye-bye.